The world is running out of computing capacity. That is a direct, literal warning from Microsoft CEO Satya Nadella. He's basically saying that Moore's Law, the old rule that computing power reliably doubles every couple of years, it's finally running out of steam. If we actually want to keep pushing the boundaries, especially in fields like artificial intelligence, we've hit a wall, a physical bottleneck. And simply building a slightly better version of the microchips we have today, that's not going to cut it anymore. We need a complete, ground-up revolution in how machines process information. We need quantum computing. Welcome to this explainer. I am so excited to guide you through this today because, honestly, we're looking at a topic that sounds like pure science fiction, but is literally unfolding right now in corporate labs all over the globe. We're going to explore exactly how this mind-boggling subatomic physics is set to completely shatter our current cybersecurity frameworks and totally disrupt traditional business as we know it. So let's jump right in and see exactly how we're going to break this all down. Here is our roadmap for today. 1. The computing capacity crisis. 2. Entering the quantum realm. 3. Real-world quantum milestones. 4. The imminent cybersecurity threat. And 5. Breakthroughs disrupting traditional business. All right, let's kick things off with part 1, the computing capacity crisis, the end of Moore's Law. To really grasp why quantum computing is such a massive deal, there's this absolutely brilliant metaphor from Seth Lloyd. He says that a classical computation is like a solo voice. It's just one line of pure tones succeeding each other, right? It's linear. It's one step at a time. But a quantum computation, that is like a symphony, many lines of tones interfering with each other. Imagine trying to perform a Beethoven masterpiece by humming just one single note at a time, versus having an entire orchestra playing simultaneously. That exponential leap from a single voice to a full, booming symphony, that is the real promise of quantum power. Moving on to part 2, entering the quantum realm, subatomic mechanics. So how do we actually build this symphony? Well, the core difference is right at the heart of the machine. Conventional computers use binary bits. Think of a standard light switch. It's either on or it's off, a 1 or a 0. That's it. Every email you send, every video you stream, it's really just millions of ones and zeros flipping back and forth. But a quantum computer uses what we call qubits. And because of the totally bizarre rules of quantum mechanics, a qubit doesn't actually have to choose. It can exist as a 1 and a 0 at the exact same time, along with all sorts of states in between. This means instead of processing possibilities one by one, a quantum computer processes a massive number of possibilities all at once. But here's the thing. Qubits do not work alone. And this brings us to an even wilder concept, quantum entanglement. This is a phenomenon where pairs or groups of particles actually become linked. You literally can't measure them independently anymore. Their state depends entirely on the other particles in their group. And get this, they can transfer information between each other instantly, even if they are, theoretically at least, an unlimited distance apart. Einstein actually really struggled with this concept, famously calling it spooky action at a distance. But today, computer scientists are betting that harnessing this exact entanglement property is what's going to let us build machines millions of times more efficient than anything available today. Which leads us to part 3, real-world quantum milestones, accelerating progress. It's wild to look back and see how fast this progress has accelerated. I mean, the mere possibility of quantum computing was only first proposed by physicist Richard Feynman back in 1982. Just over a decade later, in 1994, mathematician Peter Shor proved mathematically how it could be used to crack encryption. Fast forward to 2003, and DARPA brought the very first operational quantum network online. Then, the commercial world suddenly woke up. In 2012, 1QBit, the first dedicated commercial quantum business, set up shop in Canada. And by 2016, IBM launched its Q service, literally offering quantum computing via the cloud. In fact, they recently upgraded that system to 20 qubits of processing power. We have gone from theoretical physics on a chalkboard to cloud-accessible quantum services in just a few decades. All right, part 4, the imminent cybersecurity threat, cracking the code. Now, I want you to stop and ask yourself something. Is your digital data actually safe? Right now, your bank accounts, your private messages, corporate trade secrets, they are all protected by encryption. But that encryption relies entirely on mathematical problems that are just too incredibly time-consuming for traditional computers to solve. But what happens when the computer is no longer traditional? Well, that brings us right back to Peter Shor's 1994 demonstration. Decades ago, he laid out the mathematical proof showing exactly how quantum computing could be used to absolutely crack the common encryption standards of the time. And here is the major takeaway for us. Many of those exact same encryption standards are still the ones protecting our data today. That symphony of qubits we talked about earlier, it can process the vast combinations required to break these codes in a mere fraction of the time. This right here is exactly why major governments and massive corporations are currently in an absolute sprint to develop quantum-resistant security. The threat is not hypothetical at all. The math has been proven for nearly 30 years. Let's look at Part 5, Breakthroughs Disrupting Traditional Business. But look, this insane processing power isn't just about breaking passwords. It is going to spark unbelievable innovation. If you're sitting there thinking this is all still years away from impacting real business, just look at the organizations already utilizing D-Wave's quantum infrastructure right now. We're talking Google, NASA, and Lockheed Martin. These are absolute heavyweight entities that rely on solving the most complex optimization, search, and engineering problems in human history. They aren't waiting around for the future. They are integrating quantum infrastructure into their actual operations today. This is a massive, clear signal that the disruption of traditional business computing is already underway. So the really crucial point here is understanding which industries are going to get transformed first. Physicist Jeremy O'Brien pretty much hits the nail on the head. He predicts that in less than 10 years, quantum computers are going to start outperforming everyday computers. And the immediate result of that? Massive, game-changing breakthroughs in artificial intelligence and the rapid discovery of new pharmaceuticals. Just imagine a computer that can perfectly simulate molecular structures without needing years of physical trial-and-error lab testing. That is exactly how the next wave of life-saving drugs will be found. The ability to process data at a subatomic level lets us simulate the natural world in ways we have quite literally never achieved before. Now, before we wrap up, I have to share one absolutely mind-bending logistical reality about running these machines. Negative 460 degrees Fahrenheit, or, negative 273 degrees Celsius. That is the temperature that the cores of D-Wave quantum computers operate at. Guys, that is just 0.02 degrees away from absolute zero. Because to keep these subatomic particles in a stationary state so they can actually be measured and manipulated, they require one of the most extreme freezing physical environments in the known universe. Frankly, it's an unbelievable engineering feat just to keep the machine turned on. And that brings us to our final, and probably most provocative thought. We know quantum computers work, right? But the deepest mechanics of why they work still challenge our fundamental understanding of reality. One theorized explanation for why qubits can exist in two states simultaneously is that we're actually observing them in multiple universes at the same time. Yeah, you heard me right. Physicist David Deutsch has even suggested that quantum computation will be the first technology allowing useful tasks to be performed in collaboration between parallel universes. I mean, are we actually tapping into alternate realities just to calculate new pharmaceuticals and better AI? It is a truly staggering thought. Thank you so much for joining me for this explainer. I really hope this look into the quantum realm leaves you just as fascinated as I am and totally eager to see what parallel universes we tap into next.